In the previous example, we learned how to conduct a lower tail test when the population standard deviation sigma is known, right? So now let's do another example where we continue to assume that we know the population standard deviation sigma. Suppose a professor claims that it takes less than 170 minutes on average for students to finish a test. Okay. Let's say the students argue otherwise. A sample of 25 students use a mean of 172.52 minutes. Suppose that the time it takes for all students to finish the test is normally distributed. With a standard deviation of 10.31. Let's test the professor's claim at 1%, 5%, and 10% level of significance. Okay. So, remember the first step is one where you develop your hypotheses. So in this problem, we want to test the instructor's claim. So that claim would go into the null, right? And the parameter of interest here is the population mean. How do I know that? Again, the keyword is the word average, right? So the instructor's original claim was that mu is less than 170, and then so the statement that goes into the alternative hypothesis is that mu is greater than 170, and we know that the equal sign always goes into the null, so we put the equal sign right there, and that'll be it. Now you should note that this is an upper-tailed test. Okay, so let's go ahead and list what we know. We know that the sample size is 25 because we have a sample of 25 students. A sample mean of 172.52, that's given. The population standard deviation is 10.31. How do I know this? I know this because it says that the time it takes for all students, right? This is a keyword. The time it takes for all students, when we're talking about all students, that's the population. and then the hypothesized value is 170. That's the value that goes into your hypotheses. In step 2, we want to calculate the test statistic. Okay, so our test statistic in this case, where we know the population standard deviation is equal to x bar minus the hypothesized value mu sub 0 divided by sigma x over the square root of n. So this is 172.52 minus 170 divided by 10.31 over the square root of 25. If you do the math here, you get 1.22 for the test statistic. So far so good. Now, starting at step number 3, we remember that we can do either the critical value approach or the p-value approach. We're going to do both, but let's first do the p-value approach. Okay. So step 3, you want to formulate your decision rules. Now note that we are testing at the 1% level of significance, 5% level of significance, and 10% level of significance. So alpha is equal to 0.01, 0.05, and then 0.1. The decision rule is to reject the null if the p-value is less than alpha. So now let's move on to the last step, step 4, where we try to reach our conclusions. Okay. Before we can make any conclusion, we need to know what the p-value is, right? So remember that this is an upper tail test where we know the population standard deviation. So we're going to use the z-table. So let's first draw the normal distribution, the standard normal distribution. We have a test statistic equals 1.22. If you look at the video where I talked about is formulating the decision rule using the p-value approach, we know that this is an upper tail test, and so the p-value is the area under the curve to the right of the test statistic. Okay. So the shaded area here is your p-value. Now mathematically, this is the probability that z is greater than or equal to 1.22. Now this is in the form that z is greater than or equal to something. So in order to use the standard normal table, you have to flip the inequality, right? By doing the 1 minus the probability that z is less than or equal to 1.22. So now in order to find the p-value, all you have to do is to go into the z-table, look for 1.22 on the margins, and then find the probability. Right? So let's do that and go to the our z-table. So you want to look at row 1.2 and then look under column 0.02. That gives you a probability of 0.8888. So that means that our p-value is going to be equal to 0.1112. So now we're ready to reach our conclusions. So we have level of significance of 1%, 5%, and 10%. So then the value of alpha is 0.01, 0.05, and then 0.1. Right? We only have one test statistic, so we only have one p-value. So the p-value is 0.1112 for all these cases. Okay. Now, the decision rule is we reject the null if the p-value is less than alpha. At 1% level of significance, the p-value is 0.1112, which is greater than 0.01. So at 1%, we do not reject the null. We do not reject null because p-value is greater than alpha. Now at 5%, we also do not reject the null. Right? Because again, p-value of 0.1112 is greater than alpha of 0.05. And then at 10%, we also do not reject the null. Because p-value again is greater than alpha. So that's how we do the test using the p-value approach. Let's go ahead and look at how we do this test using the critical value approach. So let's first go ahead and formulate our decision rules. The decision rule is we reject the null if our test statistic is greater than the critical value, where the critical value is equal to z sub alpha. Okay? And this rule is what it is because this is an upper tail test. Okay. So now let's try to reach our conclusion. Now, if you go back to the video where I talked about the decision rule using the critical value approach, I showed you guys that when alpha is 0.01, the critical value is z sub alpha, which is z sub 0.01, which is 2.33. Okay. Now when alpha is 0.05, then the critical value is z sub alpha, which is z sub 0.05, which is 1.645. And then when alpha is 0.1, the critical value is equal to z sub alpha, which is z sub 0.1, which is 1.28. Okay. So now let's reach our conclusions. So we have 1%, 5%, and 10%. The test statistic we only have one test statistic, right, which is 1.22. The critical values are 2.33, 1.645, and 1.28. Remember that the decision rule is we reject the null if the test statistic is greater than the critical value. So our conclusion is that we do not reject the null at 1%. Right? The reason is that the test statistic of 1.22 is less than the critical value. We also do not reject the null at 5%, again because the test statistic is less than the critical value, and we also do not reject the null at 10%, right? Because the test statistic is less than the critical value. Okay. Now, for the sake of argument, let's think of the following situation. Suppose our test statistic is equal to, and I'm going to make up a number here, right? Whatever is equal to 1.98. Okay. What will our conclusions be? So if the test statistic is 1.98 at 1%, we do not reject the null, right? Right? Because the test statistic is still less than the critical value. At 5 and at 10%, however, we reject the null. Right? Because in those cases, right, the test statistic of 1.98 is going to be greater than the critical value of 1.645 for the 5% level of significance, and greater than the critical value of 1.28 for the 10% level of significance. Okay, so that's how we do an upper tail test when we know the population standard deviation sigma. Now, one super last thing here, right? Our conclusions were that we do not reject at 1%, we do not reject at 10%, and we do not reject at 5%. So 1, 5, and 10, all three cases. You go back to the conclusions using the p-value approach. We did not reject at 1%, we did not reject the null at 5%, and we did not reject the null at 10%. So the conclusions are consistent across the two approaches.